What if I told you that the universe is expanding faster than the speed of light, and galaxies are racing away from each other in a cosmic dance we can barely comprehend? Galaxies, those colossal islands of stars, gas, and dark matter, hold secrets that defy our understanding of space and time. From supermassive black holes lurking at their centers to galaxies colliding in spectacular mergers, the universe is a stage for events so immense and mysterious they seem almost unreal. In this video, we're diving into 50 insane facts about galaxies that will shatter everything you thought you knew about the cosmos. These facts will take you on a journey through the vastness of space, revealing the beauty, chaos, and sheer scale of the universe. By the end, you'll be left in awe of the complexity and wonder of galaxies, and maybe even question your place in this ever-expanding tapestry of stars. So buckle up and get ready to explore the universe like never before. Let's begin. Now turning to our first fact, let's talk about something that might seem counterintuitive at first. Galaxies are mostly empty space. Yes, even though galaxies are home to billions of stars, planets, and cosmic dust, the vast majority of a galaxy is just that vast. The distances between stars are so enormous that if you were to shrink a galaxy down to the size of a football field, the stars would be like a few grains of sand scattered across the entire area. This emptiness isn't just a quirk of the universe, it's what defines the structure of galaxies. The immense gaps between stars mean that even in the densest parts of a galaxy, collisions between stars are incredibly rare. This emptiness also plays a crucial role in how galaxies evolve, allowing them to expand, rotate, and interact with other galaxies without everything crashing into each other. So, while galaxies may look like dense, glowing clouds of light from afar, they're actually more like cosmic ghost towns with vast stretches of nothingness separating the stars. This emptiness is a reminder of just how big and mysterious the universe truly is. Now turning to our second fact, let's dive into something truly mind-bending. The Milky Way has a supermassive black hole at its heart. This colossal object, known as Sagittarius A star, sits right in the center of our galaxy, and it's anything but ordinary. Imagine something with a mass 4 million times that of our Sun, packed into a space smaller than our solar system. That's Sagittarius A star for you. Its gravitational pull is so intense that not even light can escape it, which is why we call it a black hole. But don't let its name fool you. This black hole isn't just a cosmic vacuum cleaner. It plays a crucial role in shaping the Milky Way. Its immense gravity helps hold our galaxy together, influencing the orbits of stars and gas clouds around it. Without Sagittarius A star, the Milky Way as we know it might not exist. Scientists believe that supermassive black holes like this one are at the center of most, if not all, large galaxies, acting as the anchors that keep everything in place. So, while it might sound terrifying to have a black hole at the heart of our galaxy, it's actually a key player in the cosmic dance that keeps the Milky Way spinning. This discovery not only deepens our understanding of black holes, but also highlights just how interconnected and dynamic our universe truly is. Now turning to our third fact, let's explore one of the most dramatic events in the universe, galaxies colliding and merging. While it might sound like something out of a science fiction movie, galaxy collisions are not only real but also surprisingly common. Galaxies, despite their vast distances, are often pulled together by gravity, leading to spectacular mergers that can reshape entire cosmic structures. Take, for example, the future collision between our Milky Way and the Andromeda Galaxy. Right now, Andromeda is hurtling toward us at a speed of about 110 kilometers per second. In roughly 4 billion years, these two galaxies will meet in a cosmic dance, eventually merging into a single, larger galaxy. But don't worry, this collision won't be as chaotic as it sounds. The distances between stars are so vast that actual star collisions are incredibly rare. Instead, the galaxies will pass through each other multiple times, their gravitational forces twisting and pulling at their shapes until they finally settle into a new, unified structure. This process isn't just a one-time event, it's a fundamental part of how galaxies evolve. Many of the galaxies we see today, including some of the largest, are the result of past mergers. These collisions trigger bursts of star formation as gas clouds are compressed and ignited, creating new stars and even new solar systems. So, while galaxy mergers might seem destructive, they are actually a creative force shaping the universe into the breathtaking tapestry we see today. This fact reminds us that even in the vastness of space, change is constant and the cosmos is always in motion. Now turning to our fourth fact, let's delve into the mysterious world of dead galaxies. Unlike the vibrant, star-forming galaxies we often imagine, these cosmic structures have essentially stopped creating new stars. But what causes a galaxy to die? The answer lies in its environment and internal processes. In dense galaxy clusters, for example, galaxies can lose their gas, the raw material needed for star formation, through a process called ram pressure stripping. As a galaxy moves through the hot gas in a cluster, this gas is stripped away, leaving the galaxy with nothing to fuel new stars. Over time, the galaxy's existing stars age and grow dimmer, turning it into what astronomers call a red and dead galaxy. Elliptical galaxies, often found in these dense clusters, are classic examples of this phenomenon. They are dominated by older, redder stars and show little to no signs of ongoing star formation. Scientists study these galaxies to understand the life cycles of galaxies and the factors that lead to their death. By observing the distribution and properties of dead galaxies, researchers can piece together how the universe evolves over billions of years. This fact reminds us that even in the cosmos, life and death are part of a grand, interconnected cycle. Now turning to our fifth fact, let's journey back in time to the very edge of the observable universe. Meet GNZ 11, the oldest known galaxy ever discovered. This ancient cosmic structure is so far away that its light has traveled for an astonishing 13.4 billion years to reach us. To put that into perspective, when the light we see from GNZ 11 first began its journey, the universe itself was only about 400 million years old, a mere toddler in cosmic terms. This galaxy offers us a rare glimpse into the universe's infancy, a time when the first stars and galaxies were just beginning to form. The discovery of GNZ 11 has profound implications for our understanding of the Big Bang and the early universe. It challenges existing models of galaxy formation, suggesting that massive galaxies could form much earlier than previously thought. By studying GNZ 11, astronomers are piecing together the puzzle of how the universe evolved from a hot, dense state into the vast, structured cosmos we see today. This ancient galaxy serves as a time capsule, allowing us to peer back into an era when the universe was still in its formative stages. It's a humbling reminder of just how vast and ancient the cosmos truly is. Now turning to our sixth fact, let's explore the incredible diversity of galaxy shapes that fill our universe. Galaxies aren't just random collections of stars. They come in distinct shapes, each telling a unique story about their formation and evolution. The most iconic shape is the spiral galaxy, like our own Milky Way. These galaxies feature swirling arms of stars, gas, and dust, often radiating from a bright central core. The spiral arms are where new stars are born, making these galaxies vibrant and dynamic. Then there are elliptical galaxies, which are smooth and oval-shaped, resembling glowing footballs in space. These galaxies are often older and contain mostly aging stars, with little gas or dust left to form new ones. They're typically found in dense regions of the universe, where gravitational interactions have stripped away their star-forming material. Finally, we have irregular galaxies, which defy the neat categories of spiral or elliptical. These galaxies are chaotic in shape, often the result of collisions or gravitational disturbances that warp their structure. Irregular galaxies are fascinating because they show us how interactions between galaxies can reshape them entirely. Each galaxy shape reveals clues about its history, environment, and the forces that have shaped it over billions of years. From the elegant spirals to the enigmatic irregulars, the variety of galaxy shapes is a testament to the complexity and beauty of the cosmos. Now turning to our seventh fact, let's dive into a surprising discovery about our very own galaxy, the Milky Way. For a long time, we thought of the Milky Way as a flat, spinning disk of stars, gas, and dust. But recent observations have revealed something extraordinary. The Milky Way is actually warped like a twisted vinyl record. This warping gives our galaxy a unique, three-dimensional shape, with its outer edges bending upward on one side and downward on the other. Scientists believe this warping could be caused by interactions with smaller satellite galaxies, like the large and small Magellanic Clouds, whose gravitational pull tugs on the Milky Way's outer regions. Another possible culprit is dark matter, the mysterious substance that makes up most of the universe's mass. Dark matter's gravitational influence could be distorting the Milky Way's shape over time. Visualizations of this warped structure show a galaxy that's far from the flat disk we once imagined, adding another layer of intrigue to our cosmic home. This discovery not only changes how we see the Milky Way, but also deepens our understanding of how galaxies evolve and interact in the vastness of space. Now turning to our eighth fact, let's explore one of the most mysterious forces in the universe, dark matter. Galaxies, including our own Milky Way, are held together by something invisible yet incredibly powerful. This unseen force is dark matter, a substance that doesn't emit, absorb, or reflect light, making it completely invisible to our telescopes. So how do we know it's there? Scientists have observed its gravitational effects on visible matter, like stars and gas. For example, stars on the outer edges of galaxies move much faster than they should if only the visible matter were holding them in place. This discrepancy suggests that an enormous amount of unseen mass, dark matter, must be exerting a gravitational pull, keeping galaxies from flying apart. But what exactly is dark matter? While we don't yet know its true nature, scientists have proposed several theories. It could be made up of particles that don't interact with light or ordinary matter, or it might be something entirely different that we haven't even imagined. What we do know is that dark matter makes up about 85% of the universe's total mass, dwarfing the amount of visible matter. Without it, galaxies as we know them wouldn't exist. Visualizations of dark matter's influence often show it as a vast, invisible web enveloping galaxies, shaping their structure and guiding their evolution. This mysterious substance not only holds galaxies together, but also plays a crucial role in the large-scale structure of the universe, connecting galaxies across unimaginable distances. As we continue to study dark matter, we inch closer to unraveling one of the greatest mysteries of the cosmos. Now turning to our ninth fact, let's dive into the fiery, star-filled world of starburst galaxies. These cosmic powerhouses are unlike anything else in the universe, forming stars at a rate hundreds or even thousands of times faster than normal galaxies like our Milky Way. Imagine a galaxy where stars are being born in a frenzy, lighting up the cosmos with their brilliance. But what causes such an explosion of star formation? The answer often lies in dramatic events like galaxy collisions or close encounters with neighboring galaxies. When galaxies interact, their gravitational forces can compress vast clouds of gas and dust, triggering a burst of star formation on an epic scale. One of the most famous examples of a starburst galaxy is the Sagittarius galaxy, also known as Messier 82. Located about 12 million light-years away, this galaxy is a hotbed of star formation, with its core glowing brightly as new stars ignite. The intense radiation from these young stars heats up the surrounding gas, creating a spectacular display of light and energy. But starburst galaxies aren't just beautiful to observe, they're also crucial to our understanding of cosmic evolution. By studying these galaxies, scientists can learn how stars form under extreme conditions and how galaxies evolve over time. Starburst galaxies also play a key role in enriching the universe with heavy elements, as the massive stars they produce explode as supernova, scattering elements like carbon, oxygen, and iron into space. These elements eventually become the building blocks for new stars, planets, and even life itself. So, while starburst galaxies may be short-lived in cosmic terms, their impact on the universe is profound and far-reaching. Now turning to our 10th fact, let's explore a phenomenon that might sound like something out of a sci-fi movie: galaxies ejecting stars. Yes, you heard that right. Galaxies can actually fling stars out into the vast emptiness of intergalactic space, creating what astronomers call rogue stars. These cosmic wanderers are no longer bound by the gravitational pull of their home galaxies and instead drift freely through the darkness between galaxies. But how does this happen? The answer lies in the powerful gravitational interactions that occur within and between galaxies. When stars pass too close to a supermassive black hole or experience a close encounter with another star, they can be hurled out of their galaxy at incredible speeds, sometimes reaching hundreds of thousands of miles per hour. This process, known as stellar ejection, has fascinating implications for our understanding of galaxy dynamics. For one, it helps explain why some galaxies appear to lose mass over time. But it also raises intriguing questions about the fate of these rogue stars. Without a galaxy to call home, they wander through the cold, dark void, often traveling for billions of years before they might encounter another galaxy or star system. Some of these stars could even end up in entirely different galaxies, carrying with them the chemical signatures of their original homes. This cosmic game of gravitational pinball also affects the structure of galaxies themselves. As stars are ejected, the remaining stars and gas can shift, altering the galaxy's shape and influencing future star formation. Rogue stars also provide a unique opportunity for scientists to study the intergalactic medium, the sparse gas and dust that fills the space between galaxies. By observing the light from these stars as it passes through this medium, researchers can learn more about its composition and density. So, while rogue stars might seem like lonely outcasts, they play a crucial role in helping us piece together the complex puzzle of how galaxies evolve and interact. And who knows, somewhere out there, a rogue star might even be carrying the seeds of life, waiting to find a new home in the vast expanse of the universe. Now turning to our 11th fact, let's dive into the mind-boggling scale of the largest known galaxy in the universe, IK 1101. This colossal galaxy stretches an astonishing 16 million light-years across, making it more than 100 times wider than our own Milky Way. To put that into perspective, if the Milky Way were the size of a basketball, IC 1101 would be the size of a football stadium. Its sheer size is almost impossible to comprehend, and it holds a staggering number of stars estimated to be in the trillions, far surpassing the Milky Way's few hundred billion. But how does a galaxy grow to such an enormous size? IC 1101 is what astronomers call a supergiant elliptical galaxy, and its immense scale is the result of countless mergers with other galaxies over billions of years. Imagine a cosmic snowball rolling through the universe, gathering more and more material as it goes. Each time IC 1101 collided with another galaxy, it absorbed its stars, gas, and dark matter, growing larger and more massive with every encounter. This process of galactic cannibalism is common in the universe, but IC 1101 took it to the extreme, becoming the largest galaxy we've ever discovered. What's even more fascinating is that IC 1101 isn't just big, it's also incredibly old. Scientists believe it formed shortly after the Big Bang, making it one of the oldest galaxies in existence. Its age and size give us a glimpse into the early universe when galaxies were still forming and merging at a rapid pace. Today, IC 1101 sits at the heart of a massive galaxy cluster, surrounded by thousands of smaller galaxies that orbit it like planets around a star. Its gravitational influence is so strong that it shapes the entire cluster, pulling galaxies and gas toward it in a cosmic dance that has been ongoing for billions of years. Despite its immense size, IC 1101 is surprisingly dim compared to other galaxies. This is because its stars are spread out over such a vast area, making it less dense than smaller galaxies like the Milky Way. But don't let its faint appearance fool you. This galaxy is a true titan of the cosmos, a testament to the incredible scale and complexity of the universe. As we continue to study IC 1101, we gain valuable insights into how galaxies form, grow, and evolve over time, reminding us just how small we are in the grand scheme of things. Now turning to our 12th fact, let's explore a hidden force that shapes galaxies in ways we're only beginning to understand: magnetic fields. Yes, galaxies have magnetic fields, and they play a crucial role in how stars form, how cosmic rays travel, and even how galaxies evolve over time. These magnetic fields are invisible to the naked eye, but their influence is everywhere, weaving through the vast expanse of galaxies like an intricate cosmic web. So, how do scientists detect something as elusive as a galaxy's magnetic field? They use a technique called radio astronomy, which allows them to observe the faint radio waves emitted by charged particles as they spiral along magnetic field lines. By studying these radio emissions, astronomers can map out the structure and strength of a galaxy's magnetic field, revealing patterns that stretch across thousands of light years. These fields aren't uniform. They twist, turn, and sometimes even form loops, creating a dynamic and ever-changing magnetic landscape. But what do these magnetic fields actually do? For one, they influence the birth of stars. When clouds of gas and dust collapse to form stars, magnetic fields can either help or hinder the process. In some cases, they slow down the collapse by exerting pressure, while in others, they channel material into dense regions, sparking the formation of new stars. Magnetic fields also play a role in shaping the flow of cosmic rays, high-energy particles that zip through space at nearly the speed of light. These fields act like cosmic highways, guiding cosmic rays along specific paths and even accelerating them to incredible speeds. Interestingly, magnetic fields also leave their mark on the evolution of galaxies. Over billions of years, they can help regulate the flow of gas within a galaxy, influencing how stars form and how galaxies grow. In spiral galaxies, for example, magnetic fields often align with the spiral arms, reinforcing their structure and helping to maintain their shape. In elliptical galaxies, the fields are more chaotic, reflecting the turbulent history of these older, more evolved systems. As we continue to study galactic magnetic fields, we're uncovering new insights into the forces that shape the universe. These invisible threads connect stars, gas, and cosmic rays, weaving together the story of how galaxies live, grow, and change over time. And while we may not be able to see them directly, their impact is undeniable, reminding us that even in the vast emptiness of space, there's always more than meets the eye. Now turning to our 13th fact, let's dive into one of the most mysterious phenomena in the cosmos: dark galaxies. These are galaxies that emit little to no light, making them nearly invisible to traditional telescopes. But how can something as massive as a galaxy remain hidden? The answer lies in their composition. Dark galaxies are made up mostly of dark matter, the mysterious substance that makes up about 85% of the universe's mass but doesn't interact with light. Without stars or glowing gas to illuminate them, these galaxies are like cosmic ghosts lurking in the shadows of the universe. So how do scientists detect something they can't see? They rely on indirect methods such as observing the gravitational effects dark galaxies have on their surroundings. For example, when light from a distant object passes near a dark galaxy, its path bends due to the galaxy's gravitational pull, a phenomenon known as gravitational lensing. By studying these distortions, astronomers can infer the presence of a dark galaxy and even estimate its mass. Another method involves looking for faint traces of hydrogen gas, which can sometimes be detected using radio telescopes. These observations provide clues about the structure and distribution of dark galaxies, even if they remain invisible in optical light. But why are dark galaxies important? They offer a unique window into the role of dark matter in galaxy formation. Unlike normal galaxies, which are shaped by both dark matter and visible matter, dark galaxies are dominated almost entirely by dark matter. Studying them helps scientists understand how dark matter behaves and how it influences the evolution of galaxies. Some researchers even believe that dark galaxies could be the building blocks of larger, more familiar galaxies, providing a missing link in our understanding of cosmic history. Interestingly, dark galaxies also challenge our assumptions about what a galaxy is. Without stars or bright gas, they defy the traditional definition of a galaxy as a collection of stars bound together by gravity. Yet, they still possess the structure and mass of a galaxy, reminding us that the universe is full of surprises. As we continue to explore these invisible giants, we're uncovering new questions about the nature of dark matter and the hidden architecture of the cosmos. Dark galaxies may be elusive, but their significance is profound. They remind us that much of the universe remains unseen, waiting to be discovered. And as we peer deeper into the darkness, we're not just finding new galaxies, we're rewriting the story of how the universe works. Now turning to our 14th fact, let's explore a fascinating feature of some galaxies' multiple cores. Unlike most galaxies which have a single central core, these galaxies boast two or more cores, often as a result of past collisions and mergers. Imagine two galaxies, each with its own supermassive black hole at the center, crashing into each other. Over time, their cores can come together, creating a galaxy with multiple hearts beating at its center. One of the most striking examples of this phenomenon is NGC 6240, a galaxy that not only has two cores but three supermassive black holes. This rare configuration is thought to be the result of a complex series of mergers, where smaller galaxies were absorbed into a larger one, leaving behind their black holes. These black holes orbit each other, locked in a cosmic dance that can last for millions of years. Eventually, they may merge, releasing an enormous amount of energy in the form of gravitational waves. But what do multiple cores tell us about galaxy formation? They provide a snapshot of the chaotic and dynamic processes that shape galaxies over billions of years. When galaxies collide, their cores don't immediately merge. Instead, they interact gravitationally, sometimes forming intricate structures like double or triple cores. By studying these interactions, astronomers can piece together the history of galaxy mergers and understand how galaxies grow and evolve. Multiple core galaxies also challenge our understanding of supermassive black holes. In galaxies like NGC 6240, the presence of multiple black holes raises questions about how they coexist and influence their surroundings. Do they disrupt star formation, or do they trigger new bursts of activity? These are questions that scientists are still working to answer, and each discovery brings us closer to understanding the complex life cycles of galaxies. Galaxies with multiple cores remind us that the universe is a place of constant change and transformation. They show us that even the most massive structures in the cosmos are shaped by collisions, mergers, and the relentless pull of gravity. As we continue to study these cosmic oddities, we're not just learning about galaxies, we're uncovering the story of how the universe itself evolves. Now turning to our 15th fact, let's dive into a discovery that reveals another layer of the Milky Way's complexity. a massive halo of hot gas surrounding our galaxy. This halo, invisible to the naked eye, is a vast diffuse cloud of superheated gas that extends far beyond the Milky Way's visible disk. Imagine a glowing, invisible bubble enveloping our galaxy, stretching hundreds of thousands of light years into space. This halo isn't just a cosmic decoration, it plays a crucial role in the life and evolution of the Milky Way. So, what exactly is this halo made of? It's composed of extremely hot gas, reaching temperatures of millions of degrees. This gas is so energetic that it emits X-rays, which astronomers have detected using space-based telescopes. The halo's immense size and heat suggest that it's a remnant of the Milky Way's formation, a relic of the chaotic processes that shaped our galaxy billions of years ago. But it's not just a leftover, it's actively involved in the galaxy's ongoing evolution. One of the halo's key roles is regulating the flow of matter into and out of the Milky Way. As stars are born and die, they release gas and dust into space. Some of this material falls back into the galaxy, fueling new star formation, while some is ejected into the halo. The hot gas in the halo acts as a reservoir, storing this material and eventually recycling it back into the galaxy. This process is like a cosmic fountain, with gas flowing out of the Milky Way, cooling in the halo, and then raining back down to fuel future generations of stars. But the halo's influence doesn't stop there. It also interacts with the intergalactic medium, the thin gas that fills the space between galaxies. As the Milky Way moves through the universe, its halo sweeps up this intergalactic gas, adding fresh material to the galaxy. This influx of new gas is essential for sustaining star formation over billions of years. Without the halo, the Milky Way might have run out of fuel long ago, leaving it a dim and lifeless galaxy. The discovery of this halo has also shed light on the Milky Way's relationship with its surroundings. By studying the halo's structure and composition, astronomers can trace the history of gas flows into and out of the galaxy. They can also learn more about the Milky Way's interactions with smaller satellite galaxies, which often leave behind trails of gas as they orbit the galaxy. These interactions are like cosmic fingerprints, revealing the dynamic processes that shape galaxies over time. The Milky Way's halo of hot gas is a reminder that our galaxy is more than just a collection of stars and planets. It's a complex, interconnected system, with each component playing a vital role in its evolution. As we continue to study this halo, we're not just learning about the Milky Way, we're uncovering the intricate dance of matter and energy that drives the life cycles of galaxies across the universe. Now turning to our 16th fact, let's explore one of the most fascinating processes in the universe: how galaxies recycle material to create new stars and planets. Just like nature recycles resources on Earth, galaxies have their own way of reusing the building blocks of the cosmos. This recycling process is essential for keeping galaxies alive and vibrant over billions of years. When stars reach the end of their lives, they don't just disappear. Instead, they release gas and dust into space through processes like supernova explosions or stellar winds. This material, rich in elements like carbon, oxygen, and iron, becomes the raw ingredients for new stars and planets. But here's the incredible part: this gas and dust don't just float away into the void. Instead, they are pulled back into the galaxy by gravity, where they can be reused. Imagine a cosmic recycling plant where old stars are broken down into their basic components, and those components are then used to build something new. This process happens on an enormous scale, with entire clouds of gas and dust collapsing under their own gravity to form new stars. These newborn stars, in turn, will one day die and release their material back into the galaxy, continuing the cycle. This recycling process is crucial for sustaining star formation over billions of years. Without it, galaxies would eventually run out of the gas needed to create new stars. Think of it like a forest that needs fallen leaves to decompose and nourish the soil for new trees to grow. In the same way, galaxies rely on the material from dying stars to fuel the birth of new ones. But the recycling doesn't stop at stars. The same gas and dust can also form planets, moons, and even the building blocks of life. Elements like carbon and oxygen, which are essential for life as we know it, are created in the hearts of stars and spread throughout the galaxy when those stars die. This means that every atom in your body was once part of a star that lived and died long before our solar system even existed. The recycling process also helps explain why galaxies like the Milky Way are still forming stars today, even though they are billions of years old. By continuously reusing material, galaxies can keep the cycle of star formation going, ensuring that they remain dynamic and ever-changing. As we continue to study this process, we gain a deeper understanding of how galaxies evolve over time. The recycling of material is a reminder that the universe is not static. It's a living, breathing system, constantly transforming and renewing itself. And just like the stars, we are all part of this incredible cosmic cycle. Now turning to our 17th fact, let's dive into a phenomenon that might sound like something out of a science fiction movie: galactic cannibalism. Yes, some galaxies are literally cannibals, consuming smaller galaxies to grow larger and more massive. This process, known as galactic cannibalism, plays a crucial role in shaping the structure and evolution of galaxies across the universe. So, how does this cosmic feast work? Larger galaxies, often with stronger gravitational pulls, can capture and absorb smaller satellite galaxies that come too close. When this happens, the stars, gas, and even dark matter from the smaller galaxy are gradually pulled into the larger one. Over time, the smaller galaxy is completely assimilated, leaving behind only faint traces of its existence, like streams of stars or distorted structures. One of the most famous examples of this process is happening right in our own cosmic backyard. The Milky Way is currently consuming several smaller satellite galaxies, including the Sagittarius dwarf spheroidal galaxy. As this smaller galaxy orbits the Milky Way, its stars are being stripped away and added to our galaxy's halo. This process has been going on for billions of years and will continue until the smaller galaxy is completely absorbed. But why does this happen? Galactic cannibalism is driven by gravity, the same force that holds galaxies together. When a smaller galaxy gets too close to a larger one, the gravitational pull of the larger galaxy overwhelms the smaller one, tearing it apart. This process not only helps larger galaxies grow, but also redistributes material throughout the universe, influencing star formation and the overall structure of galaxies. Evidence of galactic cannibalism can be seen in the form of tidal streams, long trails of stars and gas that are left behind as a smaller galaxy is torn apart. These streams can stretch for thousands of light years and are often the only remnants of the smaller galaxy's existence. By studying these streams, astronomers can piece together the history of galaxy interactions and better understand how galaxies evolve over time. Galactic cannibalism also plays a key role in the growth of supermassive black holes at the centers of galaxies. When a smaller galaxy is absorbed, its gas and stars can feed the black hole, causing it to grow even larger. This process can trigger intense bursts of star formation and even lead to the creation of active galactic nuclei, some of the most energetic objects in the universe. As we continue to explore the cosmos, we're discovering that galactic cannibalism is a common and essential process in the life cycle of galaxies. It's a reminder that the universe is a dynamic and ever-changing place, where even the largest structures are shaped by the interactions of smaller ones. And just like the stars, we are all part of this grand cosmic dance. Now turning to our 18th fact, let's explore a fascinating feature of some galaxies: their long, flowing tails of gas and stars. These cosmic tails, often stretching for thousands of light years, are not just beautiful to look at but also tell us a lot about the dynamic interactions between galaxies. So, how do these tails form? They are usually the result of gravitational interactions between galaxies. When two galaxies pass close to each other, their gravitational forces can pull and stretch material from one or both galaxies, creating these long, trailing tails. This process is similar to how the tides on Earth are caused by the gravitational pull of the Moon, but on a much larger and more dramatic scale. One of the most famous examples of a galaxy with a prominent tail is the Tadpole Galaxy. This galaxy has a tail that extends over 280,000 light-years, making it one of the longest known tails in the universe. The tail is made up of gas, dust, and stars that were pulled away from the main body of the galaxy during a close encounter with another galaxy. Over time, this material can form new stars and even smaller satellite galaxies, adding to the complexity of the galactic structure. These tails are not just remnants of past interactions, they also provide valuable insights into the dynamics of galaxies. By studying the composition and movement of the material in these tails, astronomers can learn about the forces at play during galaxy collisions and mergers. For example, the presence of young stars in a tail can indicate that the interaction triggered a burst of star formation, while the distribution of gas can reveal how material is redistributed during these events. In addition to their scientific value, these tails are also a testament to the ever-changing nature of the universe. They remind us that galaxies are not static objects but dynamic systems that evolve over time through interactions with their surroundings. As we continue to observe and study these cosmic tails, we gain a deeper understanding of the processes that shape the galaxies we see today. So, the next time you look at an image of a galaxy with a long, flowing tail, remember that you're seeing the aftermath of a cosmic dance, a dance that has been shaping the universe for billions of years. And as we move forward, we'll uncover even more about these incredible structures and the stories they tell. Now turning to our 19th fact, let's zoom out from individual galaxies and explore the vast cosmic neighborhood our Milky Way calls home. Did you know that our galaxy is part of something much larger, a supercluster? This immense structure, known as the Laniakea supercluster, is home to not just the Milky Way but also thousands of other galaxies, all bound together by gravity. So, what exactly is a supercluster? Imagine a cosmic web where galaxies are connected like beads on a string, forming clusters, and those clusters are further linked into even larger structures called superclusters. Laniakea, which means immense heaven in Hawaiian, spans an astonishing 500 million light-years and contains around 100,000 galaxies. It's like a sprawling city of galaxies, with the Milky Way being just one of its many residents. But how do scientists map something so vast? They use a technique called cosmic flow mapping, which tracks the movement of galaxies. Galaxies aren't just drifting randomly, they're pulled by the gravitational forces of nearby massive structures. By studying these movements, astronomers can trace the paths of galaxies and identify the boundaries of superclusters like Laniakea. It's like mapping the currents of a cosmic ocean. The discovery of Laniakea has profound implications for our understanding of the universe's large-scale structure. Superclusters are the largest known structures in the universe, and they help us see how matter is distributed across the cosmos. They also reveal the influence of dark matter, which plays a crucial role in shaping these immense networks of galaxies. Being part of Laniakea reminds us that the Milky Way is just a tiny piece of a much grander cosmic puzzle. It's humbling to think that our galaxy, with its billions of stars and planets, is just one small thread in this vast tapestry. And as we continue to explore superclusters like Laniakea, we gain a deeper appreciation for the interconnectedness of the universe and the forces that shape it. So the next time you gaze up at the night sky, remember that you're not just looking at stars. You're looking at a small part of an immense supercluster, a cosmic neighborhood that stretches across hundreds of millions of light-years. And as we move forward, we'll uncover even more about these colossal structures and the mysteries they hold. Now turning to our 20th fact, let's explore a mysterious and elusive type of galaxy that challenges everything we thought we knew about the cosmos. These are the so-called ghost galaxies, faint and nearly invisible structures that are incredibly difficult to detect. Unlike the bright, star-filled galaxies we're used to seeing, ghost galaxies emit very little light, making them almost like cosmic phantoms drifting through the universe. One of the most famous examples of a ghost galaxy is Dragonfly 44, discovered in 2016. This galaxy is located in the Coma cluster, about 330 million light-years away. Despite being roughly the same size as the Milky Way, Dragonfly 44 is so dim that it was almost missed entirely. In fact, it emits less than 1% of the light our galaxy does. How is that even possible? The answer lies in its composition. Dragonfly 44 is made up mostly of dark matter with very few stars. This makes it incredibly faint, but also incredibly fascinating. Ghost galaxies like Dragonfly 44 challenge our understanding of how galaxies form and evolve. For decades, astronomers believed that galaxies needed a certain amount of visible matter, stars, gas, and dust to hold themselves together. But ghost galaxies flip that idea on its head. They show us that galaxies can exist with almost no visible matter at all, held together almost entirely by dark matter. This raises big questions. How do these galaxies form? Why do they have so few stars? And what role does dark matter play in their survival? The discovery of ghost galaxies has opened up a whole new area of research. Scientists are now using advanced telescopes and techniques to hunt for more of these faint structures, hoping to uncover clues about their origins and behavior. Each new ghost galaxy we find adds another piece to the puzzle, helping us understand the diversity of galaxies in the universe and the mysterious role of dark matter in shaping them. So the next time you think about galaxies, remember that not all of them are bright and bustling with stars. Some are quiet, shadowy, and almost invisible, yet they hold secrets that could change the way we see the cosmos. And as we continue to explore these ghostly structures, we're reminded once again that the universe is full of surprises waiting to be discovered. Now turning to our 21st fact, let's dive into another fascinating feature of galaxies: massive bubbles of gas and cosmic rays. These enormous structures, often spanning tens of thousands of light-years, are some of the most dramatic and energetic phenomena in the universe. But what exactly are these bubbles and how do they form? These galactic bubbles are typically created by the intense activity of supermassive black holes at the centers of galaxies. When a supermassive black hole feeds on surrounding matter, it doesn't just swallow everything quietly. Instead, it releases enormous amounts of energy in the form of jets and winds, which push out vast amounts of gas and cosmic rays into the surrounding space. Over time, this material accumulates, forming gigantic bubbles that extend far beyond the galaxy itself. One of the most famous examples of these bubbles can be found in the galaxy Messier 87, or M87, which is home to one of the most well-studied supermassive black holes in the universe. Observations from telescopes like the Chandra X-ray Observatory have revealed two enormous bubbles of hot gas extending outward from the galaxy's center, each stretching for tens of thousands of light-years. These bubbles are filled with high-energy particles and magnetic fields, creating a dynamic and turbulent environment. But these bubbles aren't just cosmic curiosities, they play a crucial role in shaping the evolution of galaxies. By pushing gas and cosmic rays out into intergalactic space, they can regulate star formation within the galaxy. If too much gas is pushed out, it can starve the galaxy of the material needed to form new stars. On the other hand, these bubbles can also trigger star formation in certain regions by compressing gas as they expand. This delicate balance makes them a key factor in understanding how galaxies grow and change over billions of years. The discovery of these bubbles has also provided astronomers with new insights into the behavior of supermassive black holes and their impact on their surroundings. By studying the size, shape, and composition of these bubbles, scientists can learn more about the energy output of black holes and how they interact with their host galaxies. It's a reminder that even the most massive and seemingly destructive forces in the universe can have a profound influence on the cosmic landscape. So, the next time you think about galaxies, remember that they're not just collections of stars and gas, they're dynamic, ever-changing systems, shaped by forces both seen and unseen. And as we continue to explore these galactic bubbles, we uncover more about the intricate dance of energy, matter, and time that defines our universe. Now turning to our 22nd fact, let's explore a close companion of the Milky Way, the Large Magellanic Cloud. This satellite galaxy, located just about 160,000 light-years away, is one of the Milky Way's nearest neighbors and a fascinating object in its own right. Despite being much smaller than our galaxy, the Large Magellanic Cloud is a bustling hub of star formation and cosmic activity. The Large Magellanic Cloud is classified as an irregular galaxy, meaning it doesn't have the distinct spiral or elliptical shape we often associate with galaxies. Instead, it has a more chaotic, patchy appearance with bright regions of star formation scattered across its structure. These regions, known as stellar nurseries, are home to some of the most massive and luminous stars in the universe. One of the most famous examples is the Tarantula Nebula, a vast cloud of gas and dust where new stars are born at an incredible rate. This nebula alone is so bright that if it were as close to us as the Orion Nebula, it would cast shadows on Earth. But the Large Magellanic Cloud isn't just a spectacle of star formation. It also plays a significant role in the evolution of the Milky Way. As a satellite galaxy, it orbits our galaxy, and its gravitational interactions have left their mark. For instance, the Large Magellanic Cloud is thought to have pulled gas and stars from the Milky Way, creating a long stream of material known as the Magellanic Stream. This stream stretches across the sky and provides valuable clues about the history of interactions between the two galaxies. Interestingly, the Large Magellanic Cloud is also home to a variety of exotic objects, including supernova remnants, pulsars, and even a supermassive black hole candidate. These features make it a treasure trove for astronomers studying the life cycles of stars and the dynamics of galaxies. Observations of the Large Magellanic Cloud have also helped scientists refine their understanding of the cosmic distance scale, as it contains stars like Cepheid variables, which are used to measure distances across the universe. As we continue to study the Large Magellanic Cloud, we gain deeper insights into the processes that shape galaxies and the intricate relationships between them. It's a reminder that even the smaller, seemingly less significant galaxies can have a profound impact on the cosmic story. So, the next time you gaze at the night sky, remember that the Milky Way isn't alone. It has a sibling, a dynamic and vibrant galaxy that continues to shape our understanding of the universe. Now turning to our 23rd fact, let's dive into the fascinating world of ring galaxies. These unique cosmic structures are defined by their distinct ring-like appearance, setting them apart from the more common spiral or elliptical galaxies. Ring galaxies are rare and mesmerizing, offering a glimpse into the dramatic events that shape the universe. One of the most famous examples of a ring galaxy is Hoag's object, discovered by astronomer Arthur Hoag in 1950. This galaxy features a nearly perfect ring of bright blue stars surrounding a central core of older, yellowish stars. The striking contrast between the ring and the core makes Hoag's object a favorite among astronomers and space enthusiasts alike. But how do such galaxies form? The answer lies in one of the most violent processes in the cosmos: galactic collisions. Ring galaxies are often the result of a smaller galaxy passing directly through the center of a larger one. This head-on collision sends shockwaves through the larger galaxy, compressing gas and dust in its outer regions. This compression triggers a burst of star formation, creating a ring of bright, young stars. Over time, the ring expands outward, leaving behind a stunning celestial halo. The central core, meanwhile, remains relatively undisturbed, preserving the older stars that were already there. These collisions not only create beautiful structures but also provide valuable insights into galaxy dynamics. By studying ring galaxies, scientists can learn more about how galaxies interact, how star formation is triggered, and how these interactions influence the evolution of galaxies over billions of years. Hoag's object, for instance, has helped astronomers understand the role of gravitational forces in shaping galaxies and the long-term effects of galactic collisions. Ring galaxies also challenge our understanding of galaxy formation and evolution. Their unique structure suggests that not all galaxies follow the same path of development. Some may undergo dramatic transformations due to interactions with other galaxies, leading to entirely new forms and structures. This diversity highlights the complexity of the universe and the endless possibilities for discovery. As we continue to explore the cosmos, ring galaxies like Hoag's object remind us of the dynamic and ever-changing nature of the universe. They are a testament to the power of cosmic collisions and the beauty that can emerge from chaos. So, the next time you think about galaxies, remember that some of them wear their history in the form of a dazzling ring, a cosmic fingerprint of their past encounters. Now turning to our 24th fact, let's explore the mysterious world of ultra-diffuse galaxies. These galaxies are enormous in size, often as large as the Milky Way, but they are incredibly faint, emitting only a fraction of the light we'd expect from such massive structures. This low brightness makes them extremely difficult to detect, and they often appear as ghostly smudges in the night sky. One of the most intriguing examples of an ultra-diffuse galaxy is Dragonfly 17, discovered by the Dragonfly Telephoto Array. This galaxy, located in the Coma cluster, is so faint that it was almost invisible to traditional telescopes. Its discovery has opened up new questions about how galaxies form and evolve. How can something so large contain so few stars, and what role does dark matter play in holding these faint giants together? Ultra-diffuse galaxies challenge our understanding of galaxy formation because they defy many of the assumptions we have about how galaxies grow. Typically, larger galaxies are brighter with more stars and gas, but ultra-diffuse galaxies are the opposite. They are large but dim, with very little star formation. This suggests that their evolution may have been dramatically different from that of more typical galaxies. Some scientists believe that these galaxies may have lost much of their gas early in their history, preventing them from forming many stars. Others think they may have been shaped by their environment, such as being stripped of material by the gravitational pull of nearby galaxies. Dark matter also plays a key role in the story of ultra-diffuse galaxies. Despite their low brightness, these galaxies appear to contain a significant amount of dark matter, which helps explain how they maintain their structure despite having so few stars. In fact, some ultra-diffuse galaxies have been found to have dark matter halos as massive as those of much brighter galaxies. This discovery has raised new questions about the relationship between dark matter and galaxy formation, and it challenges our assumptions about how dark matter influences the evolution of galaxies. The study of ultra-diffuse galaxies like Dragonfly 17 is helping astronomers rethink what they know about the universe. These faint giants remind us that there is still so much to learn about the cosmos, and they highlight the importance of continuing to push the boundaries of our technology and understanding. As we uncover more of these ghostly galaxies, we may find new clues about the nature of dark matter, the history of galaxy formation, and the hidden complexities of the universe. So, the next time you gaze at the night sky, remember that some of the most fascinating discoveries may be hiding in the faintest glimmers of light. Now turning to our 25th fact, let's dive into the dazzling world of quasars. These are some of the brightest objects in the universe, shining with the light of trillions of stars. But what exactly are quasars? At their core, quasars are powered by supermassive black holes, often billions of times more massive than our Sun. As these black holes devour surrounding gas and dust, they release enormous amounts of energy, creating a brilliant glow that can outshine entire galaxies. Quasars are not just cosmic light shows, they are also windows into the early universe. Because they are so incredibly bright, we can see them even when they are billions of light years away. This means the light we observe from quasars today actually left them when the universe was much younger, giving us a glimpse into its formative years. By studying quasars, astronomers can learn about the conditions of the early universe, how galaxies formed, and how supermassive black holes grew to such enormous sizes. One of the most fascinating aspects of quasars is their role in galaxy evolution. The intense radiation and powerful jets of material they emit can influence the surrounding galaxy, heating up gas and preventing it from forming new stars. In some cases, quasars may even help regulate the growth of their host galaxies, acting as cosmic engines that shape the universe on a grand scale. This interplay between quasars and galaxies is a key area of research, helping us understand how the universe evolved into the complex web of structures we see today. Quasars also challenge our understanding of physics. The energy they produce is so immense that it defies our everyday experience. To put it in perspective, a single quasar can emit more energy in 1 second than our Sun will in its entire lifetime. This makes quasars not only fascinating objects of study, but also natural laboratories for testing the limits of our knowledge about the universe. As we continue to explore the cosmos, quasars remind us of the incredible power and mystery that lie at the heart of galaxies. They are a testament to the dynamic and ever-changing nature of the universe, and they inspire us to keep pushing the boundaries of what we know. So, the next time you look up at the night sky, remember that some of the most extraordinary phenomena are hidden in the distant reaches of space, waiting to be discovered. Now turning to our 26th fact, let's explore a fascinating feature of our own galaxy, the Milky Way's central bar. Unlike the flat, spiral disk we often imagine, the Milky Way has a dense, elongated structure at its core, made up of billions of stars and vast amounts of gas. This bar stretches across thousands of light years and plays a crucial role in shaping the dynamics of our galaxy. The central bar acts like a cosmic traffic controller, influencing the movement of stars and gas within the Milky Way. Its gravitational pull can funnel material toward the galaxy's center, feeding the supermassive black hole Sagittarius A and triggering bursts of star formation. This process is essential for maintaining the galaxy's structure and ensuring that new stars continue to form over billions of years. But how did this bar form in the first place? Scientists believe it's the result of gravitational instabilities within the galaxy's disk. Over time, these instabilities caused stars and gas to clump together, eventually forming the bar we see today. Interestingly, not all spiral galaxies have bars, but those that do often show signs of increased star formation and dynamic activity in their cores. The Milky Way's bar also affects the orbits of stars and gas clouds, creating unique patterns of movement. Some stars are pulled into elongated orbits that align with the bar, while others are pushed into spiral arms, contributing to the galaxy's iconic shape. This interplay between the bar and the rest of the galaxy is a key area of research, helping astronomers understand how galaxies evolve and maintain their structure over time. Visualizations of the Milky Way's bar reveal its intricate structure and the way it interacts with surrounding regions. These images not only help scientists study the bar's properties, but also give us a clearer picture of our galaxy's overall architecture. By understanding the central bar, we gain deeper insights into the forces that shape the Milky Way and the processes that drive its evolution. As we continue to map and study the Milky Way, the central bar stands as a reminder of the complex and dynamic nature of galaxies. It's a testament to the intricate balance of forces that govern the cosmos, and it highlights the ongoing processes that shape the universe around us. So the next time you gaze at the night sky, remember that even our own galaxy holds mysteries waiting to be uncovered. Now turning to our 27th fact, let's dive into the fascinating world of polar ring galaxies. These are some of the most unusual and striking structures in the universe, featuring rings of stars and gas that orbit perpendicular to the main disk of the galaxy. Imagine a spinning plate with a hula hoop tilted at a 90-degree angle around it. That's the kind of bizarre and beautiful configuration we're talking about. Polar ring galaxies are incredibly rare, and their formation is still a bit of a mystery. One leading theory suggests they form when two galaxies collide or interact gravitationally. During these interactions, material from one galaxy can be pulled out and stretched into a ring that orbits around the other galaxy at a steep angle. Over time, this ring settles into a stable, perpendicular orbit, creating the stunning polar ring structure we observe. A prime example of this phenomenon is NGC 4650A, a galaxy located about 130 million light-years away. Its bright, tilted ring of stars and gas stands out dramatically against the main disk, making it a favorite subject for astronomers studying galaxy interactions. These rings aren't just visually striking, they also provide valuable clues about the history and evolution of galaxies. By studying the motion and composition of the ring, scientists can piece together the story of the collision or interaction that created it. Polar ring galaxies also offer insights into the distribution of dark matter. The way the ring orbits the main disk can reveal how dark matter is arranged within the galaxy, helping astronomers refine their understanding of this mysterious substance. Additionally, the gas in these rings often fuels new star formation, creating bright, young stars that contrast with the older stars in the main disk. These galaxies are a testament to the dynamic and often chaotic nature of the universe. They remind us that even the most stable-looking structures can be shaped by dramatic events, and they challenge us to rethink our assumptions about how galaxies form and evolve. So the next time you picture a galaxy, don't just think of a flat, spinning disk. Imagine the possibility of a polar ring, a cosmic hula hoop spinning through the void, telling a story of collision, creation, and cosmic wonder. Now turning to our 28th fact, let's explore the vibrant world of blue galaxies. These galaxies are cosmic nurseries, teeming with young, hot stars that give them their striking blue hue. Unlike older galaxies that glow with the reddish light of aging stars, blue galaxies are bursting with energy and activity, making them some of the most dynamic places in the universe. The blue color comes from the intense radiation emitted by massive, newly formed stars. These stars burn brightly and live fast, often ending their lives in spectacular supernova explosions. This constant cycle of star birth and death makes blue galaxies a key focus for astronomers studying how stars form and evolve over time. One famous example is the Blue Pinwheel Galaxy, a stunning spiral galaxy that showcases this vibrant blue glow. Its swirling arms are dotted with regions of intense star formation, where clouds of gas and dust collapse under gravity to ignite new stars. But blue galaxies aren't just beautiful, they're also incredibly important for understanding the life cycle of galaxies. They represent a phase of intense star formation, often triggered by interactions with other galaxies or the influx of fresh gas. Over time, as the supply of gas runs out and the young stars age, these galaxies may transition into redder, more quiescent systems. By studying blue galaxies, scientists can piece together how galaxies grow, change, and eventually slow down their star formation. These galaxies also provide clues about the early universe. In the distant past, the universe was filled with young, blue galaxies as star formation was much more common. Today, blue galaxies are rarer, but they still offer a glimpse into those ancient cosmic times. They remind us that the universe is constantly evolving, with galaxies transforming from bright, star-filled nurseries into quieter, more mature systems. So the next time you see an image of a blue galaxy, Think of it as a snapshot of cosmic youth, a place where stars are born, galaxies grow, and the universe continues to unfold its mysteries. These vibrant galaxies are not just a feast for the eyes, but also a treasure trove of scientific discovery, helping us understand the forces that shape the cosmos. Now turning to our 29th fact, let's dive into the fascinating phenomenon of tidal streams. These are long, flowing trails of stars and gas that stretch across the cosmos, often resembling rivers of light in the darkness of space. But what causes these stunning structures? Tidal streams are the result of gravitational forces at work, where larger galaxies pull material away from smaller ones during close encounters or collisions. Over time, these interactions leave behind these delicate, elongated trails, which serve as cosmic fingerprints of past galaxy interactions. One of the most famous examples is the Sagittarius stream, a vast ribbon of stars that wraps around the Milky Way. This stream is the remnants of a smaller galaxy, known as the Sagittarius dwarf elliptical galaxy, which has been slowly torn apart by the gravitational pull of our own galaxy over billions of years. As the smaller galaxy orbits the Milky Way, its stars and gas are stripped away, creating this beautiful but haunting trail. The Sagittarius stream is not just a visual marvel, it's also a treasure trove of information for astronomers. By studying its structure and composition, scientists can piece together the history of the Milky Way's growth and its interactions with smaller galaxies. Tidal streams are more than just relics of destruction, they're also key to understanding how galaxies evolve. These streams provide direct evidence of the hierarchical nature of galaxy formation, where larger galaxies grow by consuming smaller ones. They also help astronomers map the distribution of dark matter, as the gravitational forces that shape these streams are influenced by the invisible dark matter halos surrounding galaxies. In a way, tidal streams are like cosmic detectives, revealing secrets about the past and present of the universe. So, the next time you gaze at an image of a galaxy, imagine the hidden tidal streams that might be weaving through the darkness. These delicate trails are a testament to the dynamic and ever-changing nature of the cosmos, where galaxies dance, collide, and reshape each other over billions of years. They remind us that even in the vastness of space, every interaction leaves a mark, and every galaxy has a story to tell. Now turning to our 30th fact, let's explore the Milky Way's stellar halo, a vast and mysterious region of old stars that surrounds our galaxy like a faint, glowing shroud. Unlike the bright, densely packed disk of the Milky Way, the stellar halo is sparse and diffuse, stretching far beyond the visible boundaries of our galaxy. But what exactly is this halo, and how did it come to be? The stellar halo is made up of some of the oldest stars in the Milky Way, many of which formed billions of years ago during the galaxy's earliest days. These stars are remnants of the chaotic processes that shape the Milky Way, including collisions with smaller galaxies and the gravitational pull of dark matter. As these smaller galaxies were absorbed by the Milky Way, their stars were scattered into the halo, creating this vast spherical cloud of ancient light. In a way, the stellar halo is like a cosmic scrapbook, preserving the history of the Milky Way's formation and growth. One of the most fascinating aspects of the stellar halo is its connection to dark matter. The halo's structure and distribution are heavily influenced by the invisible dark matter that surrounds the Milky Way. By studying the motions and positions of stars in the halo, astronomers can map the distribution of dark matter and gain insights into its role in shaping galaxies. This makes the stellar halo not just a relic of the past, but also a key tool for understanding the unseen forces that govern the universe. The Milky Way's stellar halo is also home to some of the most extreme stars in the galaxy, including ancient metal-poor stars that formed before heavier elements were abundant in the universe. These stars are like time capsules, offering a glimpse into the conditions of the early cosmos. By studying them, scientists can piece together the story of how the Milky Way evolved from a collection of gas and dust into the majestic spiral galaxy we see today. So, while the stellar halo may be faint and difficult to observe, it holds some of the most important clues about our galaxy's origins and evolution. It's a reminder that even the most unassuming parts of the universe can hold profound secrets, waiting to be uncovered by curious minds and powerful telescopes. As we continue to explore the Milky Way's halo, we're not just looking at stars, we're uncovering the story of our cosmic home. Now turning to our 31st fact, let's dive into the fascinating world of active galactic nuclei, or AGN for short. These are incredibly energetic regions found at the centers of some galaxies, powered by supermassive black holes. But what makes them so special? Well, as matter falls into these black holes, it doesn't just disappear, it heats up to extreme temperatures, releasing enormous amounts of energy in the form of light, radio waves, and even X-rays. This makes AGN some of the brightest objects in the universe, often outshining entire galaxies. The intense radiation from AGN isn't just a cosmic light show. It plays a crucial role in shaping the evolution of galaxies. The energy released can heat up surrounding gas, preventing it from cooling and forming new stars. In some cases, AGN can even blast material out of the galaxy in powerful jets, influencing the growth and structure of the galaxy over billions of years. This means that AGN aren't just passive features, they're active participants in the life cycle of galaxies. Studying AGN is no easy task, but astronomers have developed clever ways to observe them. By analyzing the light and radiation they emit, scientists can learn about the properties of the supermassive black holes at their cores, such as their mass and spin. They can also study how AGN interact with their host galaxies, shedding light on the complex relationship between black holes and galaxy evolution. In a way, AGN are like cosmic laboratories, offering insights into some of the most extreme environments in the universe. One of the most intriguing aspects of AGN is their diversity. Some are relatively quiet, emitting steady streams of radiation, while others are incredibly violent, producing jets of particles that travel at nearly the speed of light. This variety tells us that not all supermassive black holes behave the same way, and their activity depends on factors like how much matter is falling into them and the structure of their host galaxies. So, while AGN may seem like distant, mysterious phenomena, they're actually key to understanding how galaxies grow and change over time. They remind us that even the most massive and powerful objects in the universe are part of a delicate cosmic balance, shaping the galaxies we see today and influencing the universe's future. As we continue to study these active galactic nuclei, we're uncovering the dynamic processes that drive the evolution of the cosmos itself. Now turning to our 32nd fact, let's explore the intriguing world of red and dead galaxies. These galaxies have reached a point in their life cycle where they've stopped forming new stars, leaving them with an aging population of stars that give off a reddish glow. But why does this happen? Over time, galaxies can exhaust their supply of gas and dust, the raw materials needed to create new stars. Without this fuel, star formation grinds to a halt, and the galaxy becomes dominated by older, cooler stars that emit red light. Elliptical galaxies are a prime example of red and dead galaxies. Unlike spiral galaxies, which are often bustling with star formation, ellipticals are smooth, featureless, and filled with older stars. These galaxies are typically found in dense regions of the universe like galaxy clusters, where interactions with other galaxies can strip away their gas, leaving them unable to form new stars. This process gives us a glimpse into the later stages of a galaxy's life, showing how external factors can influence its evolution. The study of red and dead galaxies is crucial for understanding the life cycles of galaxies. By examining these aging stellar populations, astronomers can piece together the history of star formation in the universe and learn how galaxies transition from vibrant, star-forming systems to quiet, dormant ones. These galaxies also provide clues about the role of environment in shaping galaxy evolution, as they are often found in regions where interactions and collisions are common. Interestingly, not all red and dead galaxies stay that way forever. In some cases, a galaxy might merge with another, reigniting star formation and bringing it back to life. This shows that even galaxies that seem to have reached the end of their journey can still experience dramatic changes, adding another layer of complexity to our understanding of the cosmos. So, while red and dead galaxies might seem like the end of the story, they're actually a vital piece of the puzzle in understanding how galaxies evolve over billions of years. They remind us that the universe is constantly changing, and even the quietest corners of space have stories to tell about the forces that shape the cosmos. As we continue to study these galaxies, we uncover more about the delicate balance between creation and destruction that defines the universe. Now turning to our 33rd fact, let's dive into the fascinating phenomenon of superwinds. These are massive outflows of gas that can be ejected from galaxies at incredible speeds, often driven by intense star formation or the activity of supermassive black holes at their centers. Imagine a galaxy not just as a static collection of stars, but as a dynamic system where powerful forces can literally blow material out into the vastness of space. Superwinds are created when the energy from exploding stars, known as supernova, or the radiation from a galaxy's central black hole, pushes gas outward with tremendous force. This gas, which might otherwise be used to form new stars, is instead flung far beyond the galaxy's boundaries. These outflows can stretch for thousands of light years, creating vast streams of material that interact with the surrounding intergalactic medium. The impact of superwinds on galaxy evolution is profound. By ejecting gas, they can effectively shut down star formation in a galaxy, as the raw materials needed to create new stars are removed. This process can help explain why some galaxies, like the red and dead ones we discussed earlier, stop forming stars altogether. At the same time, superwinds can enrich the intergalactic medium with heavy elements forged in stars, spreading these building blocks of planets and life across the cosmos. Interestingly, superwinds also play a role in regulating the growth of galaxies. By expelling gas, they prevent galaxies from growing too large too quickly, maintaining a balance in the universe. These outflows can even trigger star formation in other regions, as the ejected gas collides with surrounding material and compresses it, creating new pockets of stellar activity. Visualizing superwinds can be breathtaking. Picture a galaxy with streams of glowing gas stretching out like cosmic tendrils, illuminated by the light of newborn stars or the intense radiation from a black hole. These outflows are a testament to the incredible forces at work in the universe, shaping galaxies and influencing their evolution over billions of years. So, while superwinds might seem like a destructive force, they're actually a key part of the cosmic cycle, helping to regulate star formation, enrich the universe, and maintain the delicate balance that defines the structure of the cosmos. As we continue to study these powerful outflows, we gain a deeper understanding of the dynamic processes that shape the galaxies we see today. Now turning to our 34th fact, let's explore the Milky Way's thick disk, a fascinating feature that adds depth to our understanding of our galaxy's structure. Unlike the thin, flat disk of younger stars and gas that we often picture when imagining the Milky Way, the thick disk is a region of older stars that extends above and below the main disk, giving our galaxy a layered appearance. The thick disk is thought to have formed billions of years ago, during a turbulent period in the Milky Way's history. One leading theory suggests that it was created through a series of collisions and mergers with smaller galaxies. These interactions would have stirred up the galaxy's material, causing stars to be flung into higher orbits and creating the thicker, more diffuse structure we see today. Another possibility is that the thick disk formed from the remnants of the Milky Way's earliest star-forming regions, which were more chaotic and less organized than the orderly spiral arms we observe now. What makes the thick disk particularly interesting is what it reveals about the Milky Way's past. The stars in this region are older and contain fewer heavy elements or metals compared to those in the thin disk. This suggests that they formed at a time when the universe was younger and less enriched by the heavy elements produced in later generations of stars. By studying these ancient stars, astronomers can piece together the early history of our galaxy, tracing its evolution from a chaotic, gas-rich system to the more structured spiral we know today. Visualizing the thick disk helps us appreciate the Milky Way's complexity. Imagine looking at our galaxy from the side and seeing not just a flat plane of stars, but a layered structure with a dense, bright disk surrounded by a fainter, more extended halo of older stars. This thick disk is a reminder that galaxies are not static entities but dynamic systems shaped by billions of years of cosmic events. As we continue to study the thick disk, we gain new insights into the processes that shape the Milky Way and, by extension, other galaxies in the universe. It's a testament to the intricate and interconnected nature of cosmic evolution, where even the oldest stars have stories to tell about the origins of the galaxies they call home. Now turning to our 35th fact, let's delve into the intriguing phenomenon of dust lanes in galaxies. These dark, winding regions of gas and dust are not just cosmic shadows, they play a crucial role in the life cycle of galaxies. Dust lanes are often seen cutting across the bright disks of spiral galaxies, creating striking patterns that add to their visual complexity. But beyond their aesthetic appeal, these lanes are vital to the process of star formation. Dust lanes are essentially cosmic nurseries. The gas and dust within them are the raw materials from which new stars are born. Over time, gravity causes these clouds of gas and dust to collapse, forming dense clumps that eventually ignite into stars. Without these dark, dusty regions, galaxies would lack the fuel needed to create new stellar generations. In fact, some of the most active star-forming regions in galaxies are found within or near these dust lanes, where the conditions are just right for star birth. One of the most famous examples of a galaxy with prominent dust lanes is the Sombrero Galaxy. When viewed from the side, its thick dust lane appears as a dark band encircling its bright central bulge. This feature not only makes the Sombrero Galaxy one of the most recognizable in the night sky, but also provides astronomers with a clear example of how dust lanes can shape a galaxy's appearance and evolution. By studying galaxies like the Sombrero, scientists can better understand how dust and gas interact with light, how they influence star formation, and how they contribute to the overall structure of galaxies. But how do astronomers study these dark, dusty regions? Since dust lanes absorb visible light, they are often best observed using infrared and radio telescopes. These instruments can peer through the dust, revealing the hidden processes at work. For instance, infrared observations can show the heat emitted by dust grains, while radio waves can map the distribution of gas molecules. Together, these tools allow scientists to piece together a detailed picture of how dust lanes function and their role in the broader story of galaxy evolution. Dust lanes remind us that even the darkest parts of galaxies hold the potential for creation. They are a testament to the dynamic and ever-changing nature of the universe, where even the most obscure regions play a vital role in shaping the cosmos. As we continue to explore these fascinating features, we uncover more about the intricate processes that drive the birth and evolution of stars and galaxies alike. Now turning to our 36th fact, let's explore the fascinating world of ultra-compact dwarf galaxies. These tiny cosmic powerhouses may be small in size, but they pack an incredible amount of mass into their compact forms. Imagine a galaxy that's hundreds of times smaller than the Milky Way, yet contains millions of stars crammed into a space just a few hundred light-years across. That's the essence of an ultra-compact dwarf galaxy. So, how do these dense galaxies form? One leading theory suggests that they are the remnants of larger galaxies that were stripped of their outer layers during violent collisions with other galaxies. Over time, gravitational interactions and tidal forces pull away the outer stars and gas, leaving behind a dense core that becomes an ultra-compact dwarf. Another possibility is that they formed as dense clusters of stars from the very beginning, born in regions of the universe where star formation was exceptionally intense. One of the most well-known examples of an ultra-compact dwarf galaxy is M60 UCD1, located near the massive elliptical galaxy M60. Despite its small size, M60 UCD1 is incredibly luminous with a brightness that rivals much larger galaxies. What's even more astonishing is that it harbors a supermassive black hole at its center, which accounts for a significant portion of its mass. This discovery has challenged our understanding of how black holes form and grow, suggesting that even the smallest galaxies can host these cosmic giants. Ultra-compact dwarf galaxies provide valuable insights into the processes of galaxy formation and evolution. Their extreme density and unique properties offer clues about the conditions in the early universe where such compact structures may have been more common. By studying these galaxies, astronomers can piece together the history of how galaxies grow, merge, and change over billions of years. As we continue to uncover the secrets of ultra-compact dwarf galaxies, we gain a deeper appreciation for the incredible diversity of the cosmos. These tiny yet mighty galaxies remind us that size isn't everything sometimes. The most fascinating discoveries come in the smallest packages. Now turning to our 37th fact, let's dive into the intriguing phenomenon of galaxies with long tails of gas. These cosmic structures, often stretching for thousands of light years, are like the flowing hair of the universe, shaped by the gravitational dance between galaxies. When galaxies interact or collide, their immense gravitational forces can pull streams of gas and dust out into space, creating these spectacular tails. One of the most famous examples of this is the Tidal galaxy, located about 400 million light-years away. Its long, luminous tail, which extends over 280,000 light-years, is the result of a past encounter with another galaxy. As the two galaxies passed by each other, their gravitational forces tugged at the Tidal galaxy's gas, stretching it out into a stunning tail that glows with the light of newly forming stars. This tail is not just a beautiful cosmic feature, it's also a treasure trove of information for astronomers. By studying the gas and stars within these tails, scientists can learn about the forces at play during galaxy interactions and how these events influence star formation and galaxy evolution. These gas tails also reveal the dynamic nature of galaxies. They show us that galaxies are not static islands in space but are constantly evolving, shaped by their interactions with their cosmic neighbors. The gas in these tails can eventually cool and collapse, forming new stars and even smaller satellite galaxies. In some cases, the gas may be pulled back into the galaxy, fueling future generations of star formation. The presence of gas tails also highlights the role of dark matter in galaxy dynamics. Dark matter's gravitational influence can shape the way galaxies interact, determining how gas is pulled out and distributed. By observing these tails, astronomers can infer the distribution of dark matter and better understand its role in the universe. Galaxies with gas tails remind us of the interconnectedness of the cosmos. Every interaction, every collision leaves a mark, shaping the universe in ways we are only beginning to understand. As we study these tails, we uncover the stories of galaxies past and present, piecing together the grand narrative of cosmic evolution. Now turning to our 38th fact, let's explore the Milky Way's fascinating satellite system. Our galaxy is not alone in the vastness of space. It is accompanied by a collection of smaller satellite galaxies, each orbiting the Milky Way like cosmic companions. Among the most prominent of these are the large and small Magellanic Clouds, two irregular dwarf galaxies that are visible from the southern hemisphere. These galaxies are not just beautiful sights in the night sky. They play a crucial role in the Milky Way's evolution and provide valuable insights into the dynamics of galaxy formation. The Large Magellanic Cloud, located about 160,000 light-years away, is a bustling hub of star formation. Its irregular shape and bright star-forming regions make it a prime target for astronomers studying how stars are born and evolve. The Small Magellanic Cloud, slightly farther away at around 200,000 light-years, is smaller and less active but still holds important clues about the history of our galactic neighborhood. Together, these satellite galaxies are thought to have influenced the Milky Way's structure and star formation over billions of years. One of the most intriguing aspects of these satellite galaxies is their gravitational interaction with the Milky Way. As they orbit, their gravitational pull can distort the Milky Way's outer regions, creating ripples and streams of stars and gas. These interactions can also trigger bursts of star formation within the Milky Way, as the gravitational forces compress gas clouds, leading to the birth of new stars. In some cases, the Milky Way's gravity can strip material from these smaller galaxies, creating long streams of stars and gas that stretch across the sky. Studying these satellite galaxies also helps astronomers understand the role of dark matter in galaxy formation. The distribution and motion of these galaxies suggest that they are embedded in vast halos of dark matter, which influence their orbits and interactions. By mapping their movements, scientists can infer the presence and distribution of dark matter around the Milky Way, shedding light on one of the universe's greatest mysteries. The Milky Way's satellite system is a testament to the interconnected nature of the cosmos. These smaller galaxies are not just passive companions, they are active participants in the ongoing story of our galaxy's evolution. As we continue to study them, we uncover new details about the forces that shape galaxies and the intricate dance of gravity that binds the universe together. Now turning to our 39th fact, let's dive into the fascinating phenomenon of galaxies with double nuclei. These cosmic structures are not just rare, they are windows into the violent and dynamic processes that shape galaxies over billions of years. Double nuclei occur when two galaxies collide and merge, bringing their supermassive black holes together at the center of the newly formed galaxy. Over time, these black holes may orbit each other, creating a unique double-core structure that astronomers can observe. One of the most famous examples of a galaxy with double nuclei is ARP 220, a galaxy located about 250 million light-years away. ARP 220 is the result of a colossal collision between two galaxies, and its double nuclei are a direct consequence of this merger. Each nucleus is a powerhouse of activity, with intense star formation and supermassive black holes feeding on surrounding gas and dust. The interaction between these nuclei generates enormous amounts of energy, making ARP 220 one of the brightest infrared galaxies in the universe. The presence of double nuclei provides critical insights into how galaxies evolve. When two galaxies merge, their supermassive black holes eventually spiral toward the center, drawn together by gravity. As they orbit each other, they can create ripples in the fabric of space-time known as gravitational waves. In some cases, these black holes may eventually merge, releasing a burst of energy that can be detected across the cosmos. Studying double nuclei like those in ARP 220 helps scientists understand the role of galaxy mergers in shaping the universe and the behavior of supermassive black holes. Double nuclei also reveal how galaxies recycle material during mergers. The collision of two galaxies compresses gas clouds, triggering bursts of star formation and feeding the supermassive black holes at their centers. This process can create spectacular displays of light and energy, as seen in ARP 220. By observing these interactions, astronomers can piece together the history of galaxy formation and the forces that drive cosmic evolution. Galaxies with double nuclei are a testament to the dynamic and ever-changing nature of the universe. They remind us that even the most massive structures in the cosmos are shaped by the relentless pull of gravity and the collisions of galaxies. As we continue to study these cosmic wonders, we uncover new layers of understanding about the forces that govern the universe and the intricate dance of matter and energy that defines its history. Now turning to our 40th fact, let's explore the intriguing world of green galaxies. These unique cosmic structures are in a fascinating transitional phase, caught between the vibrant activity of star formation and the quiet stillness of becoming red and dead. Green galaxies are like cosmic teenagers, no longer bursting with the energy of youth, but not yet settled into the calm of old age. Their green hue comes from the presence of ionized oxygen, which emits a specific wavelength of light that gives these galaxies their distinctive color. One of the most well-known examples of green galaxies is the green pea galaxies, a group of small, compact galaxies discovered by citizen scientists participating in the Galaxy Zoo project. These galaxies are incredibly rare, making up less than 1% of all known galaxies. Despite their small size, green pea galaxies are powerhouses of star formation, producing new stars at rates much higher than typical galaxies. Their intense activity makes them invaluable for studying how galaxies transition from being star-forming to becoming quiescent. Green galaxies play a crucial role in our understanding of galaxy evolution. They provide a snapshot of a critical phase in a galaxy's life cycle, offering clues about how star formation slows down and eventually stops. By studying these galaxies, astronomers can piece together the processes that lead to the red and dead phase, where galaxies no longer form new stars and are dominated by older, cooler stars. This transition is a key part of understanding how galaxies age and change over billions of years. The green pea galaxies, in particular, have revealed surprising insights. Their intense star formation is often accompanied by powerful outflows of gas, which can blow material out of the galaxy and into the surrounding space. These outflows may play a role in shutting down star formation by depleting the galaxy's gas reserves, the raw material needed to create new stars. This process highlights the delicate balance between the forces that drive star formation and those that bring it to an end. Green galaxies remind us that the universe is in a constant state of flux, with galaxies evolving through different stages over cosmic time. They serve as a bridge between the vibrant, star-forming galaxies of the early universe and the quiet, aging galaxies we see today. By studying these transitional objects, we gain a deeper understanding of the forces that shape galaxies and the intricate processes that govern their lives. As we continue to explore the cosmos, green galaxies offer a unique window into the dynamic and ever-changing nature of the universe. Now turning to our 41st fact, let's dive into the fascinating phenomenon of superbubbles in galaxies. These enormous cavities, often spanning hundreds or even thousands of light years, are created by the combined forces of supernova explosions and the powerful stellar winds from massive stars. Imagine a cosmic bubble, but on a scale so vast it dwarfs entire star systems. Superbubbles are not just empty spaces, they are dynamic regions filled with hot gas, cosmic rays, and shock waves that ripple through the galaxy. The formation of a superbubble begins with the birth of massive stars, which burn brightly but live short lives. When these stars reach the end of their life cycles, they explode as supernova, releasing immense amounts of energy. At the same time, the intense radiation and stellar winds from these stars push surrounding gas outward, carving out a bubble-like structure. Over time, multiple supernova and stellar winds can merge their effects, creating a single, massive superbubble. Superbubbles play a crucial role in shaping galaxies. They act as cosmic recycling centers, redistributing gas and heavy elements forged in the hearts of stars throughout the galaxy. This process enriches the interstellar medium, providing the raw materials for new generations of stars and planets. However, superbubbles can also have a more dramatic impact. In some cases, the energy from these bubbles can blow gas completely out of the galaxy, stripping it of the material needed to form new stars. This can slow down or even halt star formation in certain regions, influencing the galaxy's evolution over billions of years. One of the most striking examples of superbubbles can be found in the Large Magellanic Cloud, a satellite galaxy of the Milky Way. Here, a massive superbubble known as LMC4 spans over 1,000 light-years and is the result of countless supernova and stellar winds. Observations of this superbubble have provided astronomers with valuable insights into how these structures form and evolve, as well as their impact on the surrounding galaxy. Superbubbles also have a profound effect on the intergalactic medium, the thin gas that fills the space between galaxies. When a superbubble expels gas from a galaxy, it can inject energy and heavy elements into this medium, altering its composition and temperature. This process helps to connect galaxies to their larger cosmic environment, influencing the flow of matter and energy on a grand scale. By studying superbubbles, astronomers gain a deeper understanding of the life cycles of galaxies and the forces that drive their evolution. These massive structures remind us that galaxies are not static entities but dynamic systems, constantly shaped by the explosive power of stars. As we continue to explore the universe, superbubbles offer a glimpse into the intricate interplay between stars, gas, and the vast cosmic web that connects everything in the cosmos. Now turning to our 42nd fact, let's explore the Milky Way's galactic fountain, a fascinating cycle of gas that flows out of and back into our galaxy. Picture a cosmic fountain where gas is propelled high above the galaxy's disk, only to rain back down, creating a continuous loop of movement. This process is driven by the combined forces of supernova explosions, stellar winds, and the gravitational pull of the Milky Way itself. The galactic fountain begins when massive stars explode as supernova, or when their intense stellar winds push gas outward. This gas, heated to extreme temperatures, rises above the galaxy's disk, forming a halo of hot gas. Over time, as this gas cools, it condenses and falls back into the galaxy, much like water returning to the base of a fountain. This cycle plays a critical role in regulating star formation and shaping the galaxy's evolution. As gas flows out of the Milky Way's disk, it carries with it heavy elements forged in the hearts of stars. When this enriched gas falls back, it provides the raw materials needed to form new stars and planets. This recycling process ensures that the galaxy's star-forming regions are continually replenished, sustaining the birth of new stellar systems over billions of years. However, the galactic fountain also has a balancing effect. By removing gas from the disk, it can temporarily slow down star formation, preventing the galaxy from exhausting its resources too quickly. One of the most intriguing aspects of the galactic fountain is its connection to the Milky Way's halo, a vast region of hot gas that surrounds the galaxy. Observations have shown that this halo contains significant amounts of gas that has been ejected from the disk, only to eventually return. This interplay between the disk and the halo highlights the dynamic nature of our galaxy, where matter is constantly in motion, driven by the explosive energy of stars. The galactic fountain also has implications beyond the Milky Way. As gas is ejected into the halo, it can interact with the intergalactic medium, the thin gas that fills the space between galaxies. This interaction can influence the flow of matter and energy on a larger scale, connecting the Milky Way to its cosmic environment. By studying the galactic fountain, astronomers gain insights into how galaxies evolve and interact with their surroundings. In essence, the Milky Way's galactic fountain is a testament to the galaxy's dynamic nature. It reminds us that galaxies are not static collections of stars but vibrant systems, shaped by the continuous flow of gas and energy. As we continue to unravel the mysteries of the cosmos, the galactic fountain offers a glimpse into the intricate processes that sustain and transform galaxies over time. Now turning to our 43rd fact, let's dive into the fascinating world of tidal dwarf galaxies. These unique structures form when galaxies interact, tearing material away from each other through gravitational forces. Imagine two galaxies passing close by, their immense gravity pulling at each other, stretching out streams of gas and stars. From these streams, new, smaller galaxies can emerge, tidal dwarf galaxies. One of the most famous examples of this process can be seen in the Antennae galaxies, a pair of colliding galaxies located about 45 million light-years away. As these galaxies merge, their gravitational interactions create long, sweeping tails of gas and stars. Within these tails, dense pockets of material can collapse and form tidal dwarf galaxies. These galaxies are unique because they are born from the debris of larger galaxies, rather than forming independently in the early universe. Tidal dwarf galaxies are significant because they provide astronomers with a window into the processes of galaxy formation and evolution. Unlike typical dwarf galaxies, which are thought to form from the collapse of dark matter halos, tidal dwarfs are made primarily of ordinary matter, gas, and stars. This makes them valuable laboratories for studying how galaxies can form without the influence of dark matter. Additionally, tidal dwarf galaxies often contain young, hot stars and active star-forming regions, making them bright and easy to observe. By studying these galaxies, scientists can learn more about how star formation is triggered in different environments and how galaxies recycle material during interactions. The existence of tidal dwarf galaxies also highlights the dynamic and chaotic nature of the universe. Galaxies are not isolated islands but are constantly interacting, merging, and reshaping each other. These interactions can lead to the birth of new galaxies, the destruction of old ones, and the redistribution of matter on a cosmic scale. In essence, tidal dwarf galaxies remind us that the universe is a place of constant change and creativity. They show us that even in the chaos of galactic collisions, new structures can emerge, offering fresh insights into the processes that shape the cosmos. As we continue to explore the universe, these tiny galaxies serve as a testament to the intricate and interconnected nature of all things. Now turning to our 44th fact, let's explore the extraordinary world of ultra-luminous infrared galaxies. These galaxies are some of the brightest objects in the universe, but here's the twist: most of their light isn't visible to our eyes. Instead, they shine brightly in the infrared spectrum, emitting vast amounts of energy that we can only detect with specialized telescopes. Ultra-luminous infrared galaxies are often the result of intense cosmic events, such as galaxy collisions or mergers. When two galaxies collide, their gas and dust are compressed, triggering massive bursts of star formation. This process generates so much energy that it heats up the surrounding dust, causing it to glow brightly in infrared light. In some cases, the collision can also funnel gas toward the supermassive black hole at the center of the galaxy, powering an active galactic nucleus that adds even more energy to the mix. One of the most famous examples of an ultra-luminous infrared galaxy is ARP 220. Located about 250 million light-years away, ARP 220 is the product of two galaxies that collided and merged. This merger has created a galaxy that shines hundreds of times brighter than our Milky Way, with most of its light coming from the infrared part of the spectrum. ARP 220 is also a hotbed of star formation, producing new stars at a rate thousands of times faster than our galaxy. What makes ultra-luminous infrared galaxies so fascinating is what they reveal about the evolution of galaxies. They provide a snapshot of a critical phase in a galaxy's life, when collisions and mergers are reshaping its structure and driving intense activity. By studying these galaxies, astronomers can learn more about how galaxies grow, how star formation is triggered, and how supermassive black holes influence their surroundings. Ultra-luminous infrared galaxies also challenge our understanding of the universe. They remind us that there's more to light than what we can see with our eyes, and that the cosmos is full of hidden wonders waiting to be discovered. As we continue to explore the universe, these luminous giants offer a glimpse into the dynamic and ever-changing nature of galaxies, showing us that even in the darkest corners of space, there is light, just not the kind we're used to seeing. Now turning to our 45th fact, let's dive into the fascinating world of radio galaxies and their mysterious radio lobes. These galaxies are unlike anything you've ever seen, with enormous structures of radio-emitting material stretching far beyond their visible boundaries. These lobes can span millions of light years, making them some of the largest structures in the universe. So, what exactly are radio lobes? They are vast regions of charged particles and magnetic fields that emit radio waves, often extending far beyond the galaxy itself. These lobes are created by the supermassive black holes at the center of radio galaxies. When material falls into the black hole, it doesn't just disappear. Some of it gets ejected at nearly the speed of light in the form of powerful jets. These jets travel outward, pushing through the galaxy's gas and dust, and eventually form the massive radio lobes we observe. One of the most striking examples of a radio galaxy is Cygnus A. Located about 600 million light-years away, Cygnus A boasts radio lobes that stretch over 500,000 light-years across. These lobes are filled with high-energy particles and magnetic fields, creating a spectacular display of cosmic activity. By studying Cygnus A and other radio galaxies, astronomers can learn more about the behavior of supermassive black holes and the incredible forces they unleash. Radio lobes are not just visually stunning, they also play a crucial role in our understanding of galaxy evolution. The energy carried by these lobes can heat up the surrounding gas, preventing it from cooling and forming new stars. This process helps regulate star formation in galaxies and shapes their long-term development. Additionally, radio lobes provide a unique window into the interactions between black holes and their host galaxies, offering clues about how these cosmic giants influence their surroundings. What makes radio galaxies truly remarkable is their ability to reveal the hidden dynamics of the universe. They remind us that even the most massive and energetic processes in space can leave behind subtle traces, waiting to be discovered by those who know where to look. As we continue to explore the cosmos, radio galaxies and their lobes will undoubtedly uncover even more secrets about the universe's most powerful forces. Now turning to our 46th fact, let's explore the invisible yet powerful force that shapes our galaxy, the Milky Way's dark matter halo. While we can't see dark matter directly, its presence is felt through its gravitational influence, which extends far beyond the visible stars, gas, and dust of our galaxy. This massive halo of dark matter envelops the Milky Way, stretching hundreds of thousands of light years into space, and plays a crucial role in holding our galaxy together. So, what exactly is dark matter? It's a mysterious substance that doesn't emit, absorb, or reflect light, making it invisible to our telescopes. Yet, its gravitational pull is so strong that it keeps galaxies from flying apart. Without dark matter, the Milky Way as we know it wouldn't exist. Scientists infer the presence of dark matter by observing how stars and gas move within galaxies. The faster these objects orbit, the more mass must be present to keep them bound, and much of that mass comes from dark matter. The Milky Way's dark matter halo isn't just a passive structure, it actively shapes the galaxy's evolution. It provides the gravitational scaffolding that allows gas to accumulate and form stars, and it influences the orbits of stars and smaller satellite galaxies. Even the Milky Way's warped shape and its interactions with neighboring galaxies are shaped by the dark matter halo's immense gravitational pull. Studying dark matter is no easy task, but astronomers use a variety of techniques to map its distribution. One method involves observing the bending of light from distant objects, a phenomenon known as gravitational lensing. By measuring how light is distorted as it passes through the Milky Way's dark matter halo, scientists can create a map of its structure. Another approach is to study the motions of stars and satellite galaxies, which reveal the gravitational influence of dark matter. The Milky Way's dark matter halo is a reminder that much of the universe remains hidden from our view. Yet, through careful observation and innovative techniques, we're beginning to uncover the secrets of this invisible force. As we continue to explore the cosmos, the study of dark matter will undoubtedly reveal even more about the fundamental nature of the universe and the forces that shape it. Now turning to our 47th fact, let's dive into the fascinating phenomenon of star streams. These are long, flowing trails of stars that stretch across the cosmos, often resembling rivers of light in the darkness of space. But how do these star streams form? They're the result of smaller galaxies being torn apart by the immense gravitational forces of larger galaxies. As these smaller galaxies are pulled apart, their stars are scattered into long, delicate streams that orbit the larger galaxy, leaving behind a cosmic fingerprint of past interactions. One of the most famous examples of a star stream is the Orphan Stream, a faint trail of stars that winds its way through the Milky Way's halo. This stream is believed to be the remnants of a dwarf galaxy that was ripped apart by our galaxy's gravity billions of years ago. By studying the Orphan Stream and others like it, astronomers can piece together the history of galactic collisions and mergers, revealing how galaxies grow and evolve over time. Star streams aren't just beautiful to look at, they're also incredibly valuable to scientists. These streams act as cosmic breadcrumbs, tracing the paths of smaller galaxies that have been absorbed by larger ones. By mapping the positions and motions of stars within these streams, astronomers can reconstruct the gravitational forces at play and even estimate the distribution of dark matter in the galaxy. This makes star streams a powerful tool for understanding the invisible forces that shape our universe. The discovery of star streams has also shed light on the Milky Way's violent past. Our galaxy has likely consumed dozens of smaller galaxies over its lifetime, and the remnants of these cosmic feasts can still be seen in the form of star streams. These streams serve as a reminder that galaxies are not static, they're dynamic, ever-changing systems shaped by countless interactions over billions of years. As we continue to explore the cosmos, star streams will undoubtedly reveal even more about the history and evolution of galaxies. They're a testament to the interconnectedness of the universe and the powerful forces that drive its constant transformation. Now turning to our 48th fact, let's explore the mind-boggling world of ultramassive galaxies. These cosmic giants are among the largest and most massive structures in the universe, dwarfing even the Milky Way in both size and scale. But what makes these galaxies so extraordinary, and how do they come to be? Ultramassive galaxies like ESO 306-17 are colossal collections of stars, gas, and dark matter that stretch across millions of light years. They often reside at the centers of galaxy clusters, where they dominate their surroundings with their immense gravitational pull. These galaxies are thought to form through a combination of processes, including the merging of smaller galaxies and the accretion of gas over billions of years. As galaxies collide and merge, their stars and gas are drawn together, creating a single, massive galaxy that can contain trillions of stars. One of the most striking examples of an ultramassive galaxy is ESO 306-17, which lies about 500 million light-years from Earth. This galaxy is surrounded by a vast halo of hot gas and dark matter, and its gravitational influence extends far beyond its visible structure. By studying galaxies like ESO 306-17, astronomers can gain insights into the processes that drive galaxy growth and the role of dark matter in shaping these cosmic behemoths. Ultramassive galaxies also provide a window into the early universe. Many of these galaxies formed during a period of intense star formation and galaxy mergers, known as the cosmic noon, which occurred around 10 billion years ago. By observing ultramassive galaxies, scientists can piece together the history of galaxy formation and understand how the universe evolved from its chaotic beginnings to the structured cosmos we see today. These galaxies are not just fascinating for their size, they also challenge our understanding of physics. The sheer scale of ultramassive galaxies pushes the limits of what we know about gravity, dark matter, and the life cycles of galaxies. They remind us that the universe is full of extremes and that there is still much to learn about the forces that shape it. As we continue to study ultramassive galaxies, they will undoubtedly reveal even more about the origins and evolution of the cosmos. These galactic giants are a testament to the incredible diversity and complexity of the universe, and they inspire us to keep exploring the mysteries that lie beyond our own galaxy. Now turning to our 49th fact, let's delve into the fascinating phenomenon of galaxies with X-ray halos. These halos are massive clouds of extremely hot gas that surround certain galaxies, emitting powerful X-rays that can be detected by astronomers. But what exactly are these X-ray halos, and why are they so important in our understanding of galaxy evolution? X-ray halos are formed by gas that has been heated to temperatures of millions of degrees, often as a result of intense activity within the galaxy itself. This activity can include supernova explosions, the outflow of material from supermassive black holes, or even the gravitational interactions between galaxies in a cluster. The hot gas in these halos emits X-rays, which provide a unique window into the energetic processes shaping galaxies. One of the key roles of X-ray halos is their ability to reveal the history of a galaxy's interactions with its surroundings. For example, when galaxies collide or merge, the resulting shock waves can heat the surrounding gas, creating an X-ray halo. By studying these halos, scientists can trace the history of galaxy mergers and understand how galaxies grow and evolve over time. X-ray halos also play a crucial role in the larger ecosystem of galaxy clusters. The hot gas in these halos can act as a reservoir of material that fuels star formation or feeds supermassive black holes. At the same time, the energy released by these processes can heat the gas further, creating a feedback loop that regulates the growth of galaxies and their central black holes. One striking example of a galaxy with an X-ray halo is the massive elliptical galaxy M87, located at the center of the Virgo cluster. Observations of M87's X-ray halo have revealed intricate structures, including jets of material streaming from its supermassive black hole and shock waves rippling through the hot gas. These features provide valuable insights into the dynamic processes at work in the heart of galaxy clusters. By studying X-ray halos, astronomers can also learn more about the distribution of dark matter in galaxies. The hot gas in these halos is influenced by the gravitational pull of dark matter, and by mapping the X-ray emissions, scientists can infer the presence and distribution of this mysterious substance. This helps us better understand how dark matter shapes the structure and evolution of galaxies. X-ray halos are not just a feature of individual galaxies, they also connect galaxies to their larger cosmic environment. The hot gas in these halos can extend far beyond the visible boundaries of a galaxy, linking it to the intergalactic medium and the vast web of cosmic structure. This makes X-ray halos a vital tool for understanding the interconnected nature of the universe. As we continue to explore galaxies with X-ray halos, they will undoubtedly reveal even more about the complex processes that drive galaxy evolution. These glowing halos of hot gas are a testament to the dynamic and ever-changing nature of the cosmos, reminding us that there is still so much to discover about the universe we call home. Now turning to our 50th and final fact, let's explore one of the most dramatic events in the future of our galaxy, the inevitable collision between the Milky Way and the Andromeda Galaxy. This cosmic event, set to occur in about 4 billion years, will reshape both galaxies in ways that are both awe-inspiring and transformative. The Milky Way and Andromeda, two of the largest galaxies in our local group, are currently hurtling toward each other at a speed of about 110 kilometers per second. Despite the vast distances between them, gravity is pulling them closer, setting the stage for a monumental collision. But what exactly will happen when these two galactic giants meet? When the Milky Way and Andromeda collide, it won't be a head-on crash, but rather a slow, intricate dance over billions of years. The gravitational forces between the two galaxies will cause them to swing past each other, distorting their shapes and pulling out long streams of stars and gas. These tidal tails will stretch across the cosmos, creating a breathtaking display of cosmic chaos. As the galaxies continue to interact, they will eventually merge into a single, larger galaxy. This new galaxy, often referred to as Milkomda or Milkdromda, will be an elliptical galaxy, unlike the spiral structures of the Milky Way and Andromeda. The merger process will trigger a burst of new star formation as clouds of gas collide and compress, lighting up the galaxy with the birth of countless stars. Interestingly, the collision is unlikely to result in the destruction of individual stars or planets. The vast distances between stars mean that direct collisions are extremely rare. However, the gravitational upheaval could fling some stars out of the newly formed galaxy, sending them wandering into intergalactic space. The supermassive black holes at the centers of the Milky Way and Andromeda will also play a key role in this cosmic event. As the galaxies merge, these black holes will spiral toward each other, eventually merging into a single, even more massive black hole. This process will release tremendous amounts of energy in the form of gravitational waves rippling through the fabric of space-time. The collision between the Milky Way and Andromeda is a reminder of the dynamic and ever-changing nature of the universe. While it may seem like a distant event, it offers a glimpse into the future of our galaxy and the processes that shape the cosmos. As we continue to study these galactic interactions, we gain a deeper understanding of the forces that drive the evolution of the universe. This collision is not just a distant possibility, it's a certainty. And when it happens, it will be one of the most spectacular events in the history of our galaxy, a testament to the grandeur and complexity of the cosmos. As we conclude our journey through these 50 insane facts about galaxies, we're reminded that the universe is full of wonders waiting to be discovered. So keep exploring, keep questioning, and let the mysteries of space inspire you to look up at the stars and dream. If you enjoyed this video, don't forget to like, subscribe, and hit the notification bell for more cosmic adventures. Until next time, keep your eyes on the skies. Now turning to our conclusion, let's take a moment to reflect on the incredible journey we've just taken through 50 mind-blowing facts about galaxies. From the vast emptiness between stars to the colossal collisions that reshape entire galaxies, each fact has revealed just how dynamic and mysterious the universe truly is. These insights challenge our understanding of space, reminding us that there's still so much we don't know and so much more to discover. Galaxies are not just collections of stars and gas, they are living, evolving entities that tell the story of the cosmos. Whether it's the supermassive black holes lurking at their centers, the invisible dark matter holding them together, or the breathtaking beauty of their shapes and structures, galaxies are a testament to the complexity and grandeur of the universe. And as we've seen, even our own Milky Way is part of a much larger cosmic dance, one that will continue to unfold over billions of years. The mysteries of galaxies are endless, and each discovery brings new questions. What lies beyond the observable universe? How do galaxies form and evolve over time? And what other incredible phenomena are waiting to be uncovered? These are the questions that drive astronomers and space enthusiasts alike, and they're the same questions that invite you to keep exploring, learning, and wondering. If this journey through the wonders of galaxies has sparked your curiosity, let us know in the comments below. What fact surprised you the most? What cosmic mystery are you most eager to learn more about? Your thoughts and questions are what make this exploration so exciting, so don't hesitate to share them. And if you've enjoyed this cosmic adventure, don't forget to like, subscribe, and hit the notification bell so you never miss out on more space-related content. The universe is vast and there's always more to discover. Until next time, keep looking up at the stars and dreaming of the infinite possibilities that lie beyond. The cosmos is waiting for you.